All right, so we're going to continue with allylic bromination this morning. I want to start us out with those of us who are here. I want to start us out with a warm up, a little bit of a warm up with these resonance forms. So if you recall from organic 1, anytime you do, it says draw all possible resonance forms. Anytime you're able to do resonance, there's something that has to be present, right? You have to have a donor and an acceptor, and they have to be adjacent to one another. So a donor can be a lone pair, can be a pi bond, or we can even think of a radical being a donor, right? And this is an example of a radical, allylic radical. It's allylic because it's right next door to a double bond, right? So you have a donor, and then you also have an acceptor. Which in this case is the pi bond. Right, so the acceptor can be a pi bond or a cation. Right, so for this particular system, this allylic radical that you can see right here, right? It's a 3-carbon system, a 3-carbon unit that has a donor and an acceptor adjacent. The way you would rearrange this is just like we did the other day. So can somebody, let me see. 11 people now. Can somebody annotate the screen and show me how you would rearrange this?
Would you push the radical onto the double bond?
Okay. When you say onto the double bond, what do you mean by that?
Like you take the arrow from the dot and put it on the double bond.
Okay, let's think about what the purpose of resonance is. Let's back up a second. So the reason that resonance occurs is to take an electron or pair of electrons or charge and to spread it out over multiple atoms. That's why the donor and the acceptor have to be connected. So for this radical, you wouldn't put it here. That would violate the resonance rules. Plus, the carbon itself is not going to be able to accept that pair of electrons. But what you could do, and what happens for allylic radicals, is you take the double bond and you split it. You put one so half of that bond, which would be 1 electron, would come here. Let me change colors right quick. Will come here. And then now we'll move this radical here, that 1 electron there, to show what we're actually doing, which is shifting the double bond to that position. And then we'll have a single unpaired electron on the other carbon of that allylic system. So let me draw it. So now your double bond is here, and then your radical is here. If that makes sense, right? And then you can do it again. You can go back and forth between. That's why when you do resonance, you use a double-sided arrow, because you can go back and forth between these 2 resonance forms, right? So the allylic radical always rearranges the same way, right? You have an electron coming here, you have 1 coming here from the pi bond, and then the other electron in the pi bond goes onto the other carbon in that allylic system, because you got 3 carbons here, right? So anytime you have an allylic radical, it's going to rearrange that way. So it'll be like so. And you can interchange between them, interconvert between them. All right. What about this next example? Where's my allylic system, my allylic radical system? Where is it? And then how can we show it rearranging? Thank you for your input too. I'm not sure who that was. I couldn't see the person speaking, but thank you for your input. All right.
So one would be similar to the first one, in the sense of it's going to attack that top right one, the top right.
So right here.
Yeah.
Mhm.
So that one's going to break the double bond and attach to that carbon on the right. And it's Danielle.
Okay. All right. Thank you. So is this the same? It's not going to change.
No, it's the
The
same.
flow of electrons is always, if it's an allylic radical, the flow of electrons will always be the same. It will not change. So I'm gonna put that there and put this double bond here. Can we do it again? Do you see that same system again?
Yes.
Yeah. So you're able to do the same thing again, right? This is coming here, that's coming there, and this here. And please notice the tips of my arrows are not double-headed, right? Radicals are moved by using what's called a fishhook or a single-headed arrow. So this is 1 electron. And if I want to move 2 electrons, I use a regular arrow, a double-sided arrow, a double-headed arrow. That's moving 2 electrons, right? But that new resonance form is going to look like this, right? Well, that electron is going to be here, the double bond here, and then this double bond here, right? And then you can obviously interconvert between these. So you, the same way you went forward, forward is relative, right? But the same way we went forward, we can go the opposite direction. All right. How many times do you think we can do resonance with this last structure? All right. Kind of as a rule of thumb, if you add up the donors and the acceptors, that should be the minimum number of resonance forms that you get. It kind of differs when you have cations, when you have cations, it kind of differs. But for the most part, if you add up the donors and the acceptors, so you got a radical here that we just said could be a donor, and then 1, 2, 3, 4 pi bonds as acceptors. So at minimum, you're going to see 5 resonance forms. All right, at minimum. So where's the first allylic system, and how do we get this thing started? And I'm gonna stop here because I want to get back into allylic bromination. So I want you to finish the other ones, but we'll do the first one. All this is pattern recognition. You see a pattern of an allylic radical. When you see that, it's automatic that you can do resonance, right? That's automatically understood that you can do resonance. If it's an allylic radical, an allylic anion, or an allylic cation, you can do resonance with that. And feel free to annotate if you have that capability. Somebody can put the arrows in for this first resonance form. Right? It's not going to change. We're going to do the same exact thing we did with the other radicals. Right? This electron is now going to be here, and this double bond here. All we're doing is taking that electron and sharing it over those 3 atoms that are highlighted. That's the purpose of doing resonance. One of the purposes. right? Resonance is basically, it shows you all the possible Lewis structures of a given molecule, right? So all these different the Lewis structures is, once you build it, which we already have it, we can show that there are multiple forms of that Lewis structure. If resonance is possible. All right, so I want you to finish the rest of these. So let me put the double bonds back in. Otherwise, all right. So this is the next system. So I want you to finish those. All right. So let's go back. Let's go. Any questions about that? This is just a refresher, a review from Organic 1. Again, resonance is a vital skill. You need that. You need to be able to, you need to know your functional groups, and you need to know, a modicum of the reactions that were taught. You might not remember all the reactions, but certain reactions you definitely should remember. But resonance and identifying functional groups are two really key skills that you need from part 1. That's part of that working knowledge that I have in the syllabus, a working knowledge of part 1. All right, let's go to this problem down here, and it asks a couple of questions. And we can answer 1, 2. We can answer 1 and 2 right away. So number 1 asks, how many allylic sites are present? How do we determine that? What is allylic? And how do we determine what an allylic site is? Don't all speak out at once now. We may crash the internet. So the way to identify the allylic site, find your double bond, and then look for carbons that are attached to it, right? So this site will be allylic. Change colors right quick. And so with this carbon right here. All right. All allylic means is adjacent to a double bond. So how many allylic sites do we have?
Wouldn't it only be 1? Because it's only 1 like double bond and 1 thing that's adjacent to double bond.
Well, we have 2 carbons circled though, right? We have a carbon right here that's circled, that's adjacent and attached to that double bond. And we have a carbon right here. All right, so there actually are 2 allylic sites. Thank you for your input. There are 2 sites. Now, how do we determine the next question? How many products are possible? I gave you a way to do that on Wednesday of last week, maybe Friday. It was Friday, never mind. How do we know how many products we're going to get? Let me scroll back up. So anytime you're doing allylic bromination, if you have 1 allylic site, then the number of products is going to be 2 times that. So we have 2 allylic sites. That means we're going to have a potential for 4 products. All right, so 1, we're going to say 4. 4 possible, right? How do we get to those four products? I know it's Monday, but help me out. How do we get to those four products? When we talked about this mechanism on Friday, we said that two of the products are going to come from where? Matter of fact, we can go back up to it. Okay, good. Speak up. I can hear you.
Rearrangement.
Rearrangement, right? That happens in which step? Do you remember which step that happens in?
The third one, second.
Second step, the propagation step. So two of your products are going to be direct. Come on, iPad. And then two from rearrangement. I'm just going to abbreviate. Yeah. Screen is acting real trippy. All right, so now it asks us, look at 3, 4, and 5. Propose a mechanism, which we can do. Draw every possible resonance structure for the intermediates form of propagation, which we're going to do. Draw every possible termination product, which we'll do. And then we'll answer this question last. Which one is formed fastest? If you watch the Allylic Bromination video, can you answer that question right now in a generic sense? Like which product, if you're doing allylic bromination and you have these allylic radicals that you made in propagation, which product is going to form fastest in termination? It's a very generic answer. Right? Allylic bromination always happens faster when the product is, when the radical is less substituted, so less crowded. So we'll look at, when we go through the mechanism, we're going to see which product that'll be. Let me put this on a blank page. All right, so you can see the star materials, NBS, and light, right? We need that. What is the NBS for? Anybody? What do we use that to generate? There's gonna be a lot of dead air on YouTube. What's the purpose of NBS? Like, let's back up. What reaction is this? It's allylic bromination. So what is the purpose of NBS? Let's go back up to Friday, what we did on Friday. This is NBS and bromosuccinimide. The purpose of NBS is to generate a bromine radical. That's why you have it. That's your source of bromine in the reaction.
And you said that was because you don't run out of bromine, right?
Yeah, you won't run out, because the NBS, again, even if you start with 1 mole of NBS, it's Avogadro's number of molecules of NBS. So you're not going to run out. That's a great point. And you're right. All right, let's go back to here. And we're gonna start with this mechanism. What's the first step again? In any radical chain reaction, what's the first step in the mechanism? There are three steps, right? There's initiation, right? There's propagation, and then there's termination. So in the initiation step, this is where MBS gets cleaved into so this is MBS. I'm going to shine light on it. What type of cleavage is that again? When I break the bond and give one electron to each atom in the bond? Anybody remember that? On Friday, we discussed that is homolytic. Just like if you bring two radicals together, is homogenic. Lytic means to cut or to break. Genic means to form. All right, let's go back to here. So we got the initiation step out of the way. What's the next step in a radical chain reaction?
The propagation.
Propagation. I don't know why the screen is acting like this. I'm just gonna put P. It's in the notes from Friday, so I'm just gonna abbreviate it. So in the propagation step, that's when I take my radical or my start material. I'm just gonna let me redraw it right quick, and I'm going to that bromine is gonna basically find those allylic sites and operate on them. In the allylic bromination video, what is it about the allylic site that makes it so much more reactive than say the site that's next to it, right? So why is the allylic site more reactive than say this site right here, or even the site that's right there on the double, those hydrogens on that double bond? Why is that the case? All right, we're going to come back to that question. That's a question you should be able to answer. But we'll come back to it. All right, if you see here, let's do this one down here first. This is one of my allylic sites. Right here, it's the carbon that's adjacent to the double bonds. We're gonna do this one first, take it, react it with bromine, with a bromine radical. How does that reaction take place? Anybody? That's another question you should be able to answer. Right, it's happening through what's what we call abstraction. So we're removing removal of a hydrogen radical, H dot. Right? I had a professor in grad school that hated that term H dot, but I mean that's what we're taking off. All right. And how does that happen? Anybody?
The radical makes new radicals.
Yes, you're gonna make a new radical. I agree with that. But so let's say this is what's really happening. We're gonna break the CH bond homolytically. All right, so I'm gonna extend that bond out some. We're gonna break this CH bond. And we're gonna do it homolytically. Right? And we're gonna use bromine to do it. So if we break the CH bond like so, and then we bring in bromine to pick up the hydrogen, that's how abstraction happens. Right? You have a CH bond or some bond, and you want, if you're removing, in this case, a hydrogen radical, you break the CH bond. Everything is homolytic. Everything is one electron each. So when we're in this propagation step of a radical chain reaction, right? This is what's happening on every hydrogen, every hydrogen that's reactive enough for bromine to remove it. Let's put it that way. All right, so I don't want to redraw that whole thing. So I'm just gonna abbreviate because the backside is not reacting anyway. So this is CH2, and now this is CH2, but now it's a radical. And then one of the side products of this is HBr. This screen has me feeling like a freaking kindergarten, right? Good Lord. Let's redraw this. So that's the new radical that we just made. I'm just abbreviating this part, right? Where's my other allylic site on this in this structure?
The CH2 on the top.
Yes. One second. So it's the CH2 here, right? So we can show that. Let's show that in another propagation step. I'm just gonna abbreviate this again. This CH3 down here doesn't get touched this time, so I'm gonna leave that. It's these hydrogens right here that are gonna be abstracted. And it's the same process. Exact same process. Right, I'm gonna break this CH bond like so, homolytically. And that bond breaking is facilitated by bromine. Right, so now my new radical on this side is gonna look like this. So that's the new radical, and then plus HBr. All right, so now with all this being said and done, right, each one of those radicals has a resonance form. So I'm gonna move this piece down because both of these are gonna do resonance. Once you get to that radical and you make it, going to rearrange. Now, it may not necessarily rearrange into a more stable radical, but the fact that you can do resonance is going to happen. All right. So what is this? What would the resonance form for this top radical look like? How would you rearrange that? Anybody? Here's the pattern.
We're gonna break the double bond again,
Yes.
and that radical is gonna come up and meet with the other arrow. Yeah.
Okay, good. Excellent. So now my resonance form is going to look like this. Remember, this was a CH2 out here now. If you see a double bond that's terminal like that, it's understood that there's a CH2 at the end of it. So that's that. So now I have this radical. Anybody not see that? All right. Now, what about this one? What do I do? Here's the pattern. Doesn't change. It's an allylic radical. I'll do the same thing here that I did up top. That electron flow does not change. So now the double bond is going to be here. And then this is CH2 with a radical. This CH3 right here doesn't change. We don't touch that. So now we have, these are 4 radicals that are going to go into termination and give us our products. So we got 4 different products that we can expect. And we can answer that last question about which one forms the fastest, which one forms the slowest, so on and so forth. So let's do that. Let's add another page. We'll do the termination step. Copy these. Clean this up, and then we can do the right. So non-termination, each one of these is going to react with a bromine. How do we show that reaction? What do the arrows look like? anybody.
The two radicals are going to meet each other.
Yes. So here, I'm going to show these two coming together, right? Same thing is going to happen in each one of these steps. The two radicals are going to combine and give you a product. So up top, as you can see, the bromine, I'm going to be putting a bromine on this carbon. That's the whole purpose of the reaction. The very first thing that we started talking about is how to make alkyl halides, right? We made them from alcohols. Now we're using a different method, which is allylic bromination. And in the product, that's going to look like this. This is going to be CH2Br. Right, same thing here. And I'm abbreviating the structure. It's going to be CH2 BR, and then here, bromine is here, and then here the bromine is going to be here. These products are possible. Right? Any questions about that? All right, so the question now is which one is formed the fastest, right? And the way you determine that is you look for the least substituted radical. Right, if it's less substituted, that means it's more accessible. So all of these radicals, if you look at them, you have three out of the four radicals, three of them are primary. All right, this is primary. So is this. This is secondary. And then this is also primary. So here, you're going to really have competing processes that'll give you the one that's formed the fastest. But in this case, we have another kind of feature that's working in our favor, and it's the fact that this radical is primary, but it also has a tri-substituted double bond. Right, so that's a very stable alkene compared to the other ones. So it's probably going to be this one, due to the fact that it's a primary radical, so it's less substituted, but it's also a very stable alkene as well, right? So for alkenes, let me just go ahead and refresh that. This is an unsubstituted. This is mono substituted, di-substituted, and then tri-substituted. And then, of course, you can have a tetra-substituted. Right, and with these alkenes, the more substituted it is, the more stable it is. This is in order of increasing stability. Right, the more substituted the alkene is, the more stable it is. So over here, you can see that this alkene is here. It's got 3 carbons attached to it, so it's tri-substituted. This alkene is di-substituted. So is this one. And then so is this one. Right, you can see the 2 carbons attached to each one of those. Right, so in this case, you have primary radicals, which are the radical now, not the alkene. The radical is easily accessible because it's primary and it's unsubstituted. But the fact that you had 3 primaries to pick from, right, is not going to be a tie between all 3 of them, because one of those radicals also happens to be a tri-substituted alkene. So this is going to be the fastest, and it's going to be the most stable. All right, that won't always be the case, but for this particular example, it is. All right, any questions about that? And this is the termination step, sorry. All right. So that's this reaction, that's what happens. You have an initiation step, a propagation step, and a termination step. And within those 3 steps, you go from creation of a reactive radical, which is what happens in the first step, the initiation. And then in propagation, your reactive radical is used to make new radicals. And then in termination, the radicals that you made in propagation pair up with the halogen, that the desired halogen that you want at that allylic site. In this case, it's allylic bromination. So it's a bromine. All right, questions about allylic bromination? All right, we got about 4 minutes. Let's see what we can do with this example right here. For the following, it says draw all possible products for reaction 1 proposal mechanism. So without going through the actual mechanism, because we won't have time, we'll do it on Wednesday. How many products are possible for that alkene shown in reaction 1?
One.
You know you're gonna get 1 for sure. But you don't have to guess about that. How can we definitively say how many products we can expect? What's the first thing we need to do? If we're doing allylic bromination, what's the first thing we need to identify?
The double bonds.
Okay, where the double bond is. I agree with that. And then what else?
And carbons.
The carbons adjacent to it. So in this case, you have 2 allylic sites. How many products is that going to generate potentially?
3.
You're close.
4.
4 products, right? The number of products for allylic bromination is always 2 times the number of allylic sites, due to the fact that your allylic radicals can rearrange through resonance. All right, what about this? We're going to work these. What about this one right here? Here's my double bond. Where are my allylic sites? Is that 1?
Yes.
And that's the other one, yeah? How many products? Think about it before you answer. Because there's a requirement at that allylic site that has to be met. That top site, does it have a hydrogen on it? The site that's substituted with the methyl groups, is there a hydrogen there?
Like on the actual methyl
On the
group?
carbon? No, on the carbon,
No,
on the allylic carbon.
no.
So there's not a hydrogen there. Good. So the fact that there's no hydrogen, that means that you can't do abstraction and propagation. So for this reaction, you're only going to get two products. Right? Because only one of your allylic sites is actually going to be reactive. All right, we're going to stop here. Wednesday is going to be better. You're going to be more alert and more participatory. I'm claiming it. All right, any questions before we log out?